Oh, nobody's here. That's new. My students normally are here.
Can you give me the link?
Oh yeah, sorry. I forgot. This one doesn't look nice from this side. It's there now.
So, okay, thank you for the introduction and thank you for inviting me to this class. I am very glad to be here and to have the opportunity to try to teach you this lesson. I have to say before I start that Professor Rodrigo Yamisola is the real expert in these topics, so I will try to do my best. And if, Professor, if you find something that is not right or if you want to interfere anytime, just tell me and please don't laugh about it. So, okay, let's start. So this is the second lecture about planar robots. I suppose you have a first lecture about this. And in this lecture, we will start with robotics definition. So the idea of robots is that it's like a very general area. So it takes topics from mechanical engineering, science, computer science, electronic engineering, everything. So in robots, when you say you are a robotic expert, you are not really a robotic expert. You are an expert on some of the areas of robotics. So maybe you're an expert of the electronics of the robotics. you're an expert of artificial intelligence, you're an expert of some of the things, because robotics englobes and have a lot of different topics interconnected. So in this class, we will be talking about robot motion planning. So the idea of robot motion planning is to find the configurations of the robot that allows the robot to reach some certain destination. So first of all, what is a configuration? So in a robot, okay, we have like different joints. A joint can be, for example, this is a joint for us. This is a joint for us. Everything that we can move in our body is a joint. Okay, so a robot will have different joints, and each position of each joint is a different configuration. So this is like a configuration. This is another configuration, and so on. So what we are trying to do now is to find the configuration we need to reach some point with the robot. So we want to go from point A to point B and find the configurations we need to do this. So maybe we start here. So we move the joints in a certain way to reach this point. So that's the idea, and that's the idea of this class. And as you will see here, this is like a very mathematical problem. It's a really complex problem at the end, but you will find that it's not that hard if you understand it, okay? So first, to understand how a robot moves, we have to understand how we can move. So we can have two main types of movement. So we can have translation motion and we can have rotation. So in translation, we change our position. So we can go maybe to the right. Can you see the cursor in the screen?
Yes, sir.
Okay, perfect. Then I will use the cursor better than my arm. Thank you very much for answering. So you will see that we can go here, here, in any direction. So translational motion at the end is just moving our position, okay? The other idea or the other way of moving is rotational. So, okay, we can move, but we can also rotate. So to rotate means to change our orientation. So maybe we are in the same point, but we are facing a different way. So we are not moving from our position, but we are changing our orientation. And this is very, very important because for robots, orientation is key. Because if we want to take this bottle, we will have to do it with a certain orientation. If we go to where is the object, but with a wrong orientation, nothing will happen, okay? So you have to do it with a good orientation. So you have to do it something like that, okay? So this is like very important. All of the both kinds of movements are very relevant for robots. And the movements can be in 3 axes, X, Y, and Z. They are usually 3D movements, okay? So they are 3 axes, X, Y, and Z, and the rotations can go around this axis. So if you rotate around the X rotation or the X axis, what you are doing is changing or rotating around that axis, okay? So rotating around one axis means that you are not changing that axis. You are changing everything else. So that's the idea, okay? So as a result of this, you will have different types of movement. You can have pure translation when you just move, okay? You will have pure rotation when you just rotate. So this is like very interesting, the thing to see about pitch, roll, and yaw. This is like a way to represent orientations. So when you hear that in the movies or in aviation, they use pitch, roll, and yaw, they are just doing a rotation around a coordinate system. And finally, you will have translation and rotation, which is a combination of both. So how do we control how we move? The idea of how do we control how we move, how control how this movement is performed is that we define that movement using a reference point. So in this case, okay, this person will be at position whatever, orientation whatever, with respect to this reference point. In this case, this person will be in position whatever, orientation whatever, and this position and this orientation will be referenced with respect the same coordinate system. So when we say this, we have a reference with respect of this. So if we say this is like 50, 60, 0 position, we know that is higher than this because this was like 30, 10, 0 position. So we always have the idea is to always have the same reference to know where we are and how we are moving. And that's more or less the idea of how we want to control motion. We want to do it with respect to a coordinate system. So how do we control robot motion? How do we control robot motion? The idea of controlling robot motion, okay, is that we do it using coordinate systems. So each joint, remember that each joint is a part of the robot, okay? So you have a joint here, a joint here, a joint whatever, okay? In this case, in the robot, we have a joint here, a joint here, a joint here, a joint here, and whatever. Each joint has its self coordinate system. But now you will be asking yourself, okay, but why? The slide before, you have just told me that all the movements are with respect to the same coordinate system. Why are you telling me that now that every joint has a coordinate system? Because every joint has to be oriented. So to have a coordinate system is a way to define the translation and the rotation of every joint. So this world frame will be this reference, this universal reference that we will use to define all of the movements, which is the world frame. Okay, it's like all of the movements of the robot will be defined with respect to this world frame, which is usually the base of the robot. So when we move, we will be referencing our movements with respect this world frame. Okay, and why there is these coordinate systems? Because we need orientation, as I already told you. So this joint will have a certain position with respect to this coordinate system, and also will have a certain orientation. Because to have, imagine this joint, okay? So to have this joint in the same position, but with some orientation or another orientation, is not the same. Okay, you see the difference in my hand. So to have it like this is very different to have it like this. Although the position is the same, orientation is very important, and that's the reason why we use frames attached to each robot joint, because we require to use orientation for each joint. And at the end, you will see when if you work or you enter more in detail in kinematics of the robot, you will see that a robot, when we are designing a robot and when we are working with the robots, the thing that we require to do is that we want to define all the frames in the robot, all the frames with respect to this frame, this world frame. Okay, so we have that movement that we want to achieve with respect to the original world frame. Okay, so that's more or less the idea. Okay, and here you can see some examples of some industrial robots. I think this is the KUKA robot or the ABB robot, I'm not sure. And you can see that robots can be quite complex, okay? They have a lot of reference points. They are also links. I didn't mention about the links. A link is just the solid element that is between two joints. So the idea of a robot is that a link never changes. So it's like my bones, okay? My bones should never change unless I break my bone, it will change, but this will always be the same, okay? This distance between this and this will be always the same and should always be the same, okay? And that's important because if you know this distance, you will later know what will happen if I move like this, because I know the distance and I know how it has changed, okay? So that's more or less the idea. And here you will see different joints that can be applied to different robots. There are robots that are simpler, but there are robots that can be way too more complex with a lot of reference points, even with more than one connection to the ground. So this will be like this robot will be attached to the ground here and here, and so on. So even for this robot, there is only a one reference point that we use to define the movements of the robot. So as I already told you, what we want to do is to define our reference point for all the joints. So to define all of the reference, all of the coordinate system reference of the different joints, to define them with respect to the wall base, which will be this one, or this one, or this one, okay? This will be like the same. So we want to do that. We want to find or to define these joint coordinate systems with respect to the base reference. And for that, we can do a translation and we can do an orientation. Translation are typically encoded as a three-dimensional vector. We have X translation, Y translation, and Z translation. Okay, that's easy. We just move in one of the axes or in three of the axes of the space. So we can go in the X, Y direction, Y direction, and Z direction. In the case of rotation, things get a little bit complicated, okay? So to define a rotation, we can use a rotational matrix. That is the thing that you will see here. This is like the rotational matrix. If the rotation is with respect only one angle, you will see that this rotational matrix is quite simple to obtain. If it's between multiple angles or multiple axes at the same time, things get complicated and everything get a little bit complicated. But at the end, it's not. You will see that it's not that a big deal if you understand. So yes, we get to the point of this lesson. That is that all of this, as you can see here, is that makes controlling robot a complicated problem. We have to deal with a lot of transformations, a lot of rotations, a lot of reference points, reference frames, a lot of transformations. We have to take a lot of different things in account, and this is not easy. So now we need to find something that let us work with this. Okay, and this is where forward kinematics enter. And before I continue, I just want to ask you, I am going too fast?
Yes. Let me.
Yes, because I think I'm going.
Let's pause here a little bit.
Yes.
Before we proceed with the planar robot kinematics information, and then let me share so that I want to emphasize certain things so that they will be more ready. Okay. Let me share can you unshare for now? Rahul,
Yes.
can you
Yeah.
remove the sharing? Yeah. How come I cannot make myself? I want to do the animation. Okay. Maybe I have to.
I will make you.
Can you make me the host?
Yes.
Oh, there you go.
You are now the host.
Which one? Okay. Okay. I'm now the host. Okay. Okay. Just want to emphasize because there are some things can do with animation. I will show animation so that it will be. Okay. So first, Rahul already emphasized on the orientation, position and orientation. That's fine. And that means that we can do. How come we cannot? Shift F5. F5. It's not doing.
Maybe view.
Should be F5. How come? It's already there. There. Okay. Okay. So Rahul already. This is the one that I created these slides in Ubuntu. So I'm sorry, Rahul was not able to do to show the animation. But I just want to emphasize that you can have pure translation. That means position control. You can have pure rotation, as Rahul already mentioned, or a combination of translation and rotation. Okay. So I think that was already okay. But this one is the one that I want to emphasize. So how do we control the motion? Do you hear me? Yeah. Can you hear me?
Yes, we can hear you.
Okay, can hear me. Okay. There's no echoing. I hope there's no echoing. So, okay. So what I want to emphasize is that in the case of motion control, in this case, this person falls with respect to gravity. Probably he's a diver. Yeah, I think this is a diving board, and then he jumps and with respect or based on the forces of gravity, the person moves and was able to dive. Okay, that motion is influenced mainly by the gravity. Okay, by the forces acting on the person. That force was the initial force exerted on the board, and that propels the person to go up, and then later he was subjected to, it's always subjected to the force of gravity, and later the force of gravity pulled him down so that he will dive. Okay, that's motion according to the physical law. But in robotics, we want to control motion. We don't want to be subjected by all physical laws. Maybe sometimes you want, but most of the time we want to control our motion. Okay, so that even we can defy the forces of gravity, or we can defy the forces of nature. Okay, so how do we control motion then for things that are subjected to forces of nature? So first, well, we are doing robotics, and because that's the only tool that we are dealing with now, so we will apply robotics in this sense. Okay, so what if we attach the person to the end effector of the robot? That means the end of the robot. Okay, so this person is attached to a robotic arm. Okay, and then next, so we will move the robot. We will move the person by moving the robot. Okay, so in that sense, we can. There are some simulations or some work there in the University of Cincinnati when I went there. Some professor is doing experiments in terms of gravitational forces. So in his lab, you can simulate being in the moon, for example. So we can reduce the force of gravity on Earth. Okay, so how do we do that? We do that by attaching that person to the robot. So the robot now, we control the robot so that the person feels like he is in the moon. Okay, that's a cool way of controlling motion. Imagine the person, even for us now, for example, if you're an electrician, yeah, or fixing the street lights, an electrician fixing the lines outside. Now, if your normally we see those big trucks, yeah, that are, you know, grounded, and then you have a bucket that brings the person close to the street light so they can change the bulb, yeah, or fix some wirings. So imagine if that bucket or that truck was replaced by a robotic arm. Okay, a robotic arm where the person will feel that that he is just floating, you know, floating in the air like that. Then it will be much, the person will have a lot of control, you know, in safety and all these other things, you know, he can do. And then just, it's just like in the space, yeah, in the space shuttle where you can just play like this, you can go around, yeah, because the robot will assist the person. So the question now is, how do we control the robot so that the person can simulate or can what's the other word, can like, I don't like the word fake, but can imitate the environment where there is no gravity. So if there's no gravity, the person can really, you know, fly and fix the wiring and do this, do the cabling. Yeah. So in that sense, these are some applications where we can say that we defy the rules of physics. We defy the rules of gravity by providing a robot that will assist so that the person can feel like he's in a different world. So now that's the question. How do we control that kind of motion? So to control that kind of motion, we control the robot. Okay. So now the question, how do we control the robot then? Okay. So of course, we mentioned already, the control of the robot is just simple. It is just a control of one frame against the other frame. That's it. Finish. We're done. Whole semester done. Okay. That's it. There's nothing to it. It is the motion of one frame with respect to the other frame. That's how we control the robot. I went to my Ubuntu computer because the Ubuntu was able to do the simulate the animation, because the animation is important for you to understand. Yeah. So hold on, let me connect again. I think I'm not connected to the internet. That's why. Because none of us were doing Windows. Rahul and me are doing Windows, so we cannot run the simulation. So it's important to run, I mean, to the animation. It's important to run the animation so that we can, okay, now it's there. Let me join again. It's taking time. Okay. Okay, I think that's the only animation that I need. Then let me, there. These computers, once you decide to give up, they will suddenly work. Let me share my screen. Okay, there. So okay. So now, how do we control? How do we model? Okay, one way is how do we control motion? That's the question. Yeah, we control motion by providing a robot that will eventually control what will happen to that person or to the working piece or to anything attached to the robot with respect to the environment. That's how we control. Okay, because our only tool is the robot. So now, how do we model? When we say how do we model robot motion, is that how do we express the motion into mathematical terms? Okay, modeling is in terms of mathematical modeling. So we model everything mathematically so that we can do the necessary equation to be able to implement in computer programs the needed controller to implement our desired motion. Okay, so when we say model, it's the mathematical model. So how do we model mathematically the robot motion? Well, as I mentioned, it is the movement of one frame with respect to the other. Okay, so then, well, the robot is very complicated like this. So which frame is it? Which frame is it, sir? First of all, the way to do it is that we attach frame, just like what Dr. Rahul already mentioned this one. We attach frame to each joints of the robot. Okay, so one frame on the base, another frame on joint 1, another frame in joint 2, another frame joint 3, and another frame at the end, at the hand, or we call it an effector. Okay, so this frame with respect to that frame 2 with respect to frame 1. Okay, if we can express that, then we're done. Okay, that means if we can express frame 2 with respect to frame 1, we can also express frame 3 with respect to frame 2. We can express frame 4 with respect to frame 3. That's it. So if we will be able to do this, the movement of one frame with respect to the other, then any frame, any consecutive frame, we can model. Okay, so frame 1 with respect to frame 0, frame 2 with respect to frame 1, frame 3 with respect to frame 2, and frame 4 with respect to frame 3. But because of that mathematical model, everything just becomes matrices. Everything is a matrix. Okay, now because of those matrices, because now they're expressed mathematically, now the advantage of that is that when express things in mathematical form, these forms, these models now can be governed by mathematical laws. We can apply multiplication, addition, like this, all these things. So now, because the result of this expression of one frame moving with respect to the other frame is just a matrix. So if we do a pre-multiplication of all the matrices, matrix 1 multiplied by matrix 2 by matrix 3 by matrix 4, for example, now we can express. If we do that, the result is the expression of frame 4 with respect to the base frame. Finish. Okay, so the most critical part is the movement of one frame with respect to the other. This is what we are really trying to find here. How do we express that movement of the frame with respect to the other frame? If we can do that, everything else can be governed by mathematical equation, and everything else can be done, we can interpret, we can move everything, we can move the end effector, we can combine two robots, everything else. Okay, that's what I wanted to emphasize. Okay, now, so now these are just some examples that I showed, and Dr. Rahul already showed that if you have very complicated robot, well, don't worry about the complicatedness of that robot. All you need to do is just assign frames to each joints. That's it. No matter how many joints there are, you just assign frames to each joint and then express those frames with respect to the other. Okay? Then once you do that, what I want to emphasize here is that once you're able to assign frames, you will be able to remove now the physical robot, and you will be just remaining with frames flying in the air. No more physical robot. Now, because you're just dealing with frames, now you can convert, because those frames are modeled mathematically, everything else is a mathematical expression. No more physical robot. But whatever happens to that mathematical model will definitely happen to the physical robot, because we model that robot into our mathematical model. Okay? And so everything else governed by mathematical equation, everything else governed by physical equations,
Now, if you apply those computations of physical things moving around, of rigid bodies moving around and interacting with each other, the same thing will happen into the physical system. Okay, so that's all. And now, okay, just before we move on to the next to further to the much deeper topic, what I want to emphasize is that to express that movement of one frame with respect to the other, we already mentioned that there is a position part and there is an orientation part, okay, which we can separate. Those two things are moving independent of each other. Okay, we can choose to consider only position at one point in time, and then we can again consider orientation at another point in time. Okay, we can separate them because those two dimensions, those two entities of position and orientation are independent of each other. The same thing happens when you move X, Y, and Z, for example. Okay, the movement of X is independent of the movement of Y and also independent of the movement of Z, because all those movements, all those components along those axes are orthogonal to each other, and so they cannot influence each other. Okay, because of that, you can superimpose. That means that you can consider one at a time and then later combine them together. It's the same effect. Okay, so now I want you to look at this. Now I need annotation. Okay, so that now I want you to look at this figure here. So when we say position, okay, this is our reference frame. Okay, we move this frame 2 moves with respect to frame 1. Okay, excuse me. But when we consider position, we can consider, because of that, we can consider only the origin. That origin of this point with respect to the X, Y, and Z axis of frame 1. Okay, so how is that, sir? Well, we know that already. I mean, you know, in physics 1, you know this. There are components of this point with respect to X, Y, and Z. For example, okay, let me draw. Okay, just to remind you. Okay, that's X, and this is Y. That's Y. Okay, and Z going up and down. Okay, so the axis we can extend. So now what are the components? So for example, this point here, this point we can express to here. Okay, yeah, that's the X component. So maybe we call this one P. Okay, yeah, that's P. So P2, just say P so that it won't be too complicated. So that is the component of P with respect to X along the X axis. Okay, and then the component of P with respect to Y. Okay, do you still remember this? And component of P with respect to Z. Okay, so now that is what I'm saying. This P is this vector P. Okay, I call it here P2 with respect to 1. That means the position of frame 2 with respect to 1. But anyway, for now, just to give us less confusion, let's just say that is P, a vector P. Okay, a vector P. Okay, that defines the location of this point in a three-dimensional space, can be decomposed into 3. Okay, a component of P with respect to the X. This is that one. Maybe instead of P1, we say PX. Okay, and then component with respect to Y, PY, and component with respect to Z. Okay, so given those three components, they define the result. If you add these 3 components, they will define the resulting vector P. Okay? I hope that is clear. Okay, that is just position only. Okay? There is that point in space where the components along X, Y, and Z we can decompose in order to know what is that position of that point in a three-dimensional space. I think that one is very clear. Okay? So in order to define the position, we need therefore a vector of three components in a three-dimensional space. Okay? Well, our world, the physical world, is only three-dimensional in terms of position. Okay? And three dimensions also in terms of orientation. But for position, it's just 3D. So we say 3D movement, 3D goggles, 3D everything, 3D because there's a certain depth when you see things. But of course, this is not just 3D position, but there's also orientation. But yeah, in terms of looking, it will be 3D because your vision travels into a three-dimensional space. Okay, so that's 3D. There's a component of X, Y, and Z. So now, okay. So, any question on position of a point in space? I think that is clear. Okay, so now let's clear everything because I don't want to dwell so much with position because there's one thing that's more complicated than position, and that's orientation. Okay, and that's why now I just want to give you an idea, an overview of what is a three-dimensional position and another three-dimensional orientation so that it becomes a six-dimensional space. Okay, but later we will do a planar robot. Rahul will take over to explain the planar robot forward kinematics and inverse kinematics so that we will know where we are going. But in terms of we won't jump into the six-dimensional space because it will be very, very complicated. So let's start with small items first in terms of small things in terms of dealing with robots in the plane and not in the six-dimensional space. But anyway, I just want to give you an overview of what's going on. So in position, we say there are three components. We understand that. So now in orientation, there are in this case, three vectors. Okay, three vectors, sorry, not six, but 9 components. Okay, but some of them are redundant. For now, the rotation matrix has 9 components. So what are these? So you can also see that arguably, there are 3 vectors here. You can see that, right? So, sir, where are those 3 vectors? Well, it's easy. See? See, this is one vector. If you imagine this point to be this point here, is exactly the same principle. This point here is expressed with respect to the X, Y, and Z of frame 1. So this point expressed with respect to X, Y, and Z, this one. Okay? And another point, Y, this one with respect to X, Y, and Z is that one. Another point expressed with X, Y, and Z is that one. See? So why do you need 3 axes here? Well, 3 axes because those axes rotate. Okay. That's how do we express the rotation, okay, of these axes that are orthogonal to each other. Okay. This axis here has this point. Okay, later it's a unitary vector, yeah. But never mind. Let's just forget about unity magnitude of the vector. But just say there's that vector. Okay, there's that vector with this endpoint, and the endpoint of that vector, therefore, we can express also with respect to like this, yeah. There is. If that is, maybe we call it P, or what was that? P, maybe H. Let's just call it H. So if that is H, so this is H of X. Okay, and then this point is H of Y, and this is H of Z. So those are the 3 components. So here we can say HX, HY, and HZ. Okay, and then we repeat the process. Now, if we say this is S or H, not I, maybe S, and then the maybe U, okay, maybe, yeah. So now you have, so this is H, and this is S, and this is U. So you have SX, SY, and SZ. And then you have UX, UY, and UZ. Okay? So now, okay, one thing that I want you to just remember is that in position and orientation, there is 3 components of position. And in our case, there are 9 components of orientation. How do we come out with that? Is based on the vector. You express each vector with respect to the axis of the reference frame. Okay, finish. We're done. Okay, but we go to the details once we go with the 6-dimensional space. But for now, I just want to give you an overview that this is how position and orientation is expressed. Let's worry about it later. Okay, now let's deal with the much simpler case of the planar robot. Now, Raul can take over. How do I do this? I stop. There. Stop presenting. Where do I stop presenting? I don't see. Do you see anything? Here, stop share there.
Okay.
I didn't see it. Okay, now. Okay. Okay, now Rahul, you take over.
Can you give me the permission?
Okay, yes.
Thank you.
Make host. Okay.
Thank you. So I will start with the second part.
Sorry, Rahul. It's 2 o'clock already.
Okay.
Let's have a 10-minute break.
Okay.
And then we will come back. Okay. And then Rahul will do the second part of the planar robot. Okay. Thank you all. See you later.
Hello. Let's go back. You take over.
So let's begin again. So I will start with now the planar robot forward kinematics. As I did before, I will try to explain it the best I can, and then Rodrigo will just emphasize in the things that he thinks are best, or I'm not explaining the best, so you can totally understand it. So let's start. Okay. Okay, so we ended here. Okay, so now we know what reference frames are. We know that we have to work with them, and we know that they can be complicated. So let's start to know what is forward kinematics. So the idea of forward kinematics is that we want to compute the position of the robot and effector as a function of its joints. So for example, here, as Professor Rodrigo Yamisola said, what we want to achieve is to have the transformation between, we'll select this, between the effector reference and the base reference. Okay, so this is our goal. In forward kinematics, what we try to achieve is to represent this an effector position as a function of its joints. So for example, for this case, which is a planar robot, a planar robot is just a robot that is only in the two-dimensional space. Okay, this is a very good place to start, because it's not that hard to understand. Because if you start with a three-dimensional robot or a six-dimensional robot or something like that, you will break your head. So it is a good place to start with only 2 dimensions. So let's start with this. What will you do? You do here is that you want to put these 2 values or this position as a function of this one. And how do you do this? So the first option, which is the simplest one for this scenario, is to use geometry, to use trigonometry. So this position, if you remember in your trigonometry class, you can know that here there is a triangle, and here you have this angle, which in this case is θ1. This distance, okay, can be represented as this, okay, and this distance can be represented at this, being, sorry for the drawing, but being this angle, θ1 plus θ2. Well, this will end here actually. Sorry for the mess. That's it. So yeah, this is, let me fix that. This is, now I think it's better to understand like this. Okay, so this is θ1, this angle is θ1 plus θ2, and this angle is θ1. So now, using these 2 angles, we are able to compute this distance using this equation. So what is the x value of this position? The x value of this position is this distance plus this distance. So we already know the x value of this position, and if this angle changes, we just have to introduce the new value of the angle in this function. So if this angle is 30 degrees and goes to 40 degrees, we have only changed this value to know what is the position of the effector when we change that angle. The same goes with the y value, but instead of using the cosines, which are this distance, we use the sinus. So we use this distance, and it's the same. Okay. So as you can see here in this scenario, for a planar robot with only 2 degrees of freedom, it's quite easy. We just use cosines and sinus, and that's it. In the case of a 3-dimensional robot, things start getting complicated. Okay, so now we have this angle, and this angle. So the total angle of the total position x position of the robot will be the sum of all this distance. Okay, this will be this distance, this will be this distance, and this will be this distance. Okay, the same goes to these ones, but instead, just as the last time, we use this one, which is the sine, instead of the cosine. Okay, so that's the idea. But what happens when we have more difficult robots, when we have maybe a 4-dimensional robot or more complex robot that has different types of joints? You will see it in the future, I think, with Professor Rodrigo, and you will see that sometimes only doing geometry is not the best option, but you will have to understand things like algorithms like dynamic Hartenberg and things like that to compute this Cartesian position. But right now, this is forward kinematics, just to get the position of the robot and effector as a function of the angles of the different joints. So I don't know if this is an example that
Yes, it is an example.
So how do I run? I can run it.
Yes, I will run.
Also, if you want to stop right now to say
Yes.
something, it's better. Just to wait for the end.
Okay, hold on. We have to run the example on the on Octave. I think it is important for us to run the example so that you will understand.
I give you the permissions.
Okay. Some reason my computer today is acting up. This Ubuntu is not. Okay, ito ang Octave. My computer hang again. Okay, let me see if I can run Octave from the. This is just MATLAB, but I think this computer doesn't have MATLAB. Ah, there's MATLAB here. Oh, there's no that. I don't have the okay, it's here. So now MATLAB doesn't have license in this computer, so I need to run Octave online. Nice. Good hand. Okay, anyway, it doesn't. When things don't work, they will not work all the way. Okay. Octave online. Okay, let me share my screen. Okay. Okay, so hopefully we'll get things done here in the Octave Online, and dismiss. I need to sign in. I need to write. Can I load a script here? Let's say sign in with Google. Okay. Okay. Now can I do dismiss? Upload a file. Okay. Upload a file on this teaching. And this robot one. Okay, let's see if this one runs. Can I say robot one? Okay, it's running. So now, do you see that? It doesn't dismiss. So this is my code, which I thought I have put this one a pause. Yeah, probably I need to upload something. No. Robot 1A. Okay. This robot 1A is the one that with the pausing. Robot 1A. Okay. Let's clear. Let's clear first. Let's see. Can I not cancel everything? Okay, what I'm doing here is that there's only one planar robot. Just so the simplest example of a planar robot that Dr. Rahul showed. Sorry, this is Octave Online. It's slow in computing. Okay, I want to clear everything first before clear. Can I say CLS? No. Okay. No, it doesn't do that. Control C. I thought this is compatible with MATLAB. Okay. Robot. I want to say okay. Robot 1A. It shows this one. Okay, let me create a new. Yes, it's clear. Okay. Now, am I okay? Upload that one robot. Okay. And robot one. Okay. So in this case here, I wanted to show a 1 degree of freedom. That means 1 joint robot. So this is the joint that can you see this?
Yes.
Yeah, is it clear in the screen? Yeah, this is the joint that Dr. Rahul was discussing about. Only this time there's only 1 link. This is the origin, and this is the end of the robot. So as the joint of the robot, that means theta 1. From here, from the flat configuration, it will try to go up to increase the theta 1. So how does the graph looks like, and how is the physical robot looking like? So, excuse me, I'm trying to plot here in the graph the time with respect to the angle, or we say the elbow because it's like this. That's the elbow, and then you go like that. Okay, from flat to going up. And then the hand position. So if the elbow movement change for 1 degree of freedom, what is the position of the hand in terms of X and Y? Okay, so now, okay, well, in this case here, it is just 1 position in terms of the X, I think, because this is the time. There's this HX and HY. So in this case here, okay, let me continue so that we can see clearly what's going on. So you keep on adjusting. Say you increase the angle, and then also the angle here increases. Yeah, with the time it goes. This is just linear. It will go up. Yeah. So this angle from 0, it will go up. So this angle from 0, it will go up given time. So now, what is X and Y? So in this case, the X, that one that Dr. Rahul was the component along X and the component along Y. So the component along X, so as you can see here, X is, I think this is 1, or 0.5 is the length, or 0.45. Okay, it starts with 0.45, the length. And so 0.45, and then it becomes the X, as this one goes up, the X goes smaller. You see that? Okay, when the angle goes up, the X component becomes smaller and smaller. Yeah. So here the HY component, as the time goes further, it should go down. Okay. Okay. I'm just plotting because those are critical information. I'm plotting what is the position of the hand or the end effector when the angle changes. Okay. You cannot combine them, because there are 2 separate spaces: the joint space, it's called, and the hand space, or the operational space, or the world space. Yeah. Now, or the workspace. So now with respect to time, we will move the hand. We will increase the angle. So now the hand X move down. Increase the angle, the X moves down, and then the Y component along this direction, you can see that it's growing, it's going up. So that's why this HY goes up. Yeah. So the hand, so this is the plot of the hand with respect to the Y axis, and the hand with respect to the X axis. So if you see that in the one that Dr. Rahul was showing, this is the part that is showing, and here we can say that we are only considering the let's just do this. We're only considering the first, this one. Let's ignore this part. Okay, we are only changing the
That means that we also ignore this part. We also ignore that part. Okay. Gone. Okay. Now we only do this. So as the cosine theta becomes smaller, because cosine 0 is 1, and cosine, as your angle becomes bigger, okay, your angle becomes bigger, x goes in. Okay, so maybe if this one goes up like that, okay, maybe this is the final configuration. So in that case here, this now is your new hx, the hand position with respect to x. Originally, probably it was here. Okay, so the hand position with respect to x, okay, initially, and the hand position with respect to y, maybe at time final, yeah. So from moving here to there, so you go inward, okay. So now let's just, if we go to here, yeah, to annotate, and I could have deleted it. Okay, anyway, I don't want to delete. Let's just continue. So that is your x component, and so your x. So in the graph that we showed, given time and your hand position, okay. So if you say your hx component, so hx goes up and then it will go down, and then the y component is from 0. It starts from 0 because sine 0 is 0, and then it goes higher as the angle goes higher, like that. Okay, so now this is the hand position. So this is your hy plot, and the other one is your hx plot given time. As you're changing your angle of time with respect to theta. In this case, theta 1. So theta 1. So with time, as theta 1 increases linearly from 0 to, I think, to 60 degrees, then the plot of your hx and hy is like that. Okay, so in this case, this is the joint, we call it the joint space. Okay, the joint space. This is the plot of the joint angle with respect to time. And this case, this is the world space. Okay, what's the difference? Well, in the joint space, the axis is the joint angle. You see here, the axis is the joint angle theta 1. Well, this is time, yeah. It could be theta 1, theta 2. This could be theta 2 or theta 3. But the axis is joint value. Okay. In the world space, the axis is the hand position. Okay, the hx or hy. Okay, you can plot it in 3 dimensions also. Like maybe you can say hx, hy here, like that, depending on how you like it. Hx here and hz there. Okay, then it becomes a 3-dimensional plot. But anyway, when you're talking about the world space, you are talking about the hand position with respect to the world, and you are talking about joint space, you are talking about the joint angles. So now, if you go back to the examples, in this example, you can see that this is the actual robot as it moves from 0 to 60 degrees angle, and this is the hand position from 0 to some value of hy, and from 0.45 to some value of hx. Okay, and then your angle go, oh, this is not linear, your angle goes from 0 to 60. Okay, so that's for the single dimensional robot. Now we want to plot a 2-dimensional robot. Again, we just move in terms of forward kinematics. Forward kinematics meaning the input are the joint angles. The input are the joint angles and the output is the hand. So you give it a value of the joints, then we plot what happens to the hand. That's forward kinematics. Okay. Inverse kinematics, which later we will introduce, is then you need to find, you give it a hand position, and then you need to find what joints would allow you to, for the hand to be in that position. Okay, that's inverse. But now it's forward. So let's just say forward kinematics. You give it joint angles. We don't know where's the hand. So we just plot the hand by computing this. So you get, okay. These buttons we should give. Okay. So you give it joint angles there. It's like X as a function of theta 1 and theta 2 in this case, because there are two values. Okay. So the input, or well, we can do that X and Y. Okay. So the input is R, X, theta 1 and theta 2. And then the output is X and Y. So that's forward. You input the angles and then you know, oh, where's the hand, like that. Yeah. So you, okay, we want to just move the angles like this, and then we don't care. Now we know, we need to know where's the hand. Okay. But in the other case, we give it the hand. So that's the inverse kinematics. We take the inverse of this function. So that means that, okay, maybe, okay, the result will be joint angles, theta 1 and theta 2. So it is just the inverse of that function. We don't know for now what is that function. So the inverse of that function, and then your input is X and Y. So that means you bring the hand. Okay, bring that. Okay, I put this there, and then now we need to know. We need to measure what are the joints. Okay, like that. Okay. So for now we are doing this. Input the angles. We need to find the hand. Okay, so now we input the angles, need to find the hand. Where is it now? Let's go there. Okay, here. So now let's, that's the one joint. I mean, one joint robot. Now let's do two joints. So that's robot 2. So let's do. Is it not done yet? Oh, it's not done yet. Okay, now, so robot 2. Robot 2 meaning there are 2 degrees of freedom. Okay, so what this one does is that there, you plot, these are the joint angles. So, okay, this is the joint space. Okay, let me show you. Joint space. Okay, so in this case, I think this is theta 1 axis and theta 2 axis. Okay, so we don't include the time here, just the values of the angle. Okay, now here, this is the hand space. Okay, so this is hand position X. So this is the X and hand position Y. Okay, so we're going to move the joint 1 first. So 0, I mean joint 2 first. 0 if joint 1, that means 0 of joint 1, it's flat. Yeah, it's flat on the ground, and joint 2 will go up. So now let's see what happens. So there. Only joint 2 goes up. So only joint 2 goes up, the values. Joint 1 is 0. So it doesn't do anything. There, goes up, goes up, goes up. So it's just like now a fan, a Japanese fan. It goes from flat to going up. Okay? Okay, now let's move theta 1 a little bit. So theta 1 rise up a little bit here. So because theta 1 now is not 0, it goes up. So there again, we increment joint 2. So we're just plotting the values of the joints, okay, increasing the values of the joints. And now we're also looking at what happens to the hand, okay? So of course, it will just sweep, okay, because we change the values of the joints, so the hands will sweep like that, okay? Please pay attention because you will do this program on your own. Okay, now you increase the joint 1, so this is the next column. So we keep on increasing. Okay, so what I'm trying to show you is that as your joints values change, so this is how it will look like with respect to the hand. Okay, it's just sweeping, and in most cases, if you do that, the hand movement is not very meaningful. Okay, unless you're Japanese and you want to just, you know, fan yourself, yeah, you want to use that fan, then it's fine, yeah. But if you don't want to use a fan like movement like that, then it's not very meaningful. Okay, so that's what happens when you do this forward kinematics motion. Okay, so I think you get the idea. So now let's where are we? Are we almost? Okay, so annotate, clear all drawings. I want Rahul to take over now. Okay, let's see if I already did justice on that part. Okay, that is that part. This is the part we discussed. So as you move your joint from here. So from 0 to theta 1, like 60 degrees. So angle theta 1, it goes from 0 to some 60 degrees, about linearly. And then now what happens to the hand? So you plot the hand hx here. Hx goes from 0.45 to some value, smaller value. So 0.35 to some smaller value. And then your hy here, hy goes up, okay, from 0 to some value. Okay, that one we understand. Okay, now let's clear that. So we go to the next. Okay, so this is the one that I showed you, that once you just increment your values from 0 to something, some value from theta 1 is 0 all the time, and theta 2 increases from 0 to 150. Then theta 1 remains flat, and then theta 2, this second link will sweep there. And then you increase a little bit, theta 1 will goes up, then you sweep again, then theta 1 goes up and sweep again. Okay, that's forward kinematics to you. Once you change the joint angles, then you plot the hand movement. Okay, then that's forward kinematics. Kinematics, I already mentioned theta 1, the hand movement h1, hx, and hy. And then that is for a single joint. For two joints, theta 1, theta 2, joint 1 and joint 2, then the hand movement hx and hy. Okay, now we need to go to, okay, you take over, Rahul.
Maybe you want to finish.
Okay.
Or I can finish, but maybe.
Okay. Yes. So now, what we need to do now is that is the forward kinematics. As I mentioned, it is not very meaningful in terms of physically moving or manipulating objects, because the purpose of the robot, sometimes it is called a manipulator. Yeah, it's called manipulator because it's able to manipulate objects in space. That means that you take one. I got this one from a diamond mine hole, and you see there's a diamond there.
Oh,
yeah,
so cool.
I'm just kidding. It's not. It's not allowed. It's illegal to. I just saw this stone somewhere. Understand? Okay. Anyway, so the manipulator is that you take this object, and then the robot will bring it somewhere like that. Yeah. Now like that. Yeah. So that is what the robot arm, especially in the earlier days of robotics, robots are arms, or otherwise called manipulators, because they're able to transfer one object, move this object from here to there. So they're able to manipulate an object. So the meaningful movement, therefore, is for the hand. We need to know where is the hand in the space and move that hand to another space. So probably a pick and place movement. So pick from here and then move place here. Yeah, pick and place. Okay, so that's the basic the movement of robots, especially in the earlier days. So now, because we wanted to move the hand, now the forward kinematics is showing us this equation. So you input angles, you get the hand movement. Okay, but that is not very meaningful. Okay, what we want is you input the x. Okay, this x is a vector. Okay, in this case that's a vector, and that's also a vector. Well, just to emphasize. Okay, and there is that function, the inverse function of the forward kinematics. Okay, but this is non-linear. Okay, so we don't like that. Okay, but there's a way to go about it. Okay, instead of doing this non-linear inverse function, there is a linear, we can linearize things so that inverse function becomes linear. Okay, so because there's, to do that, we need to consider at the velocity level. What is that velocity level? This part here. That means that you need to take the partial. Okay, if you take the partial of this one, of the forward kinematics, so x is equal to f of q, for example, and you take the derivative of this with respect to time, for example. So let's say the partial of x with respect to partial of t. Okay, partial of f with respect to partial of t. Okay. Okay. So everything moves with respect to time. So they are independent. They are dependent to time. Yeah. So now, so how do we expand this one? So partial of f with respect this forward kinematics function, if you take the partial of that, will return a Jacobian matrix multiplied by the joint angle with respect to time. Okay, in this case now it becomes linear because that is a matrix and that is a vector. Okay, so in that sense, if you remove the derivative with respect to time, you can just say partial of x is equal to the Jacobian times the partial of q. That's linear. So if we inverse it, now you take partial of q is equal to the inverse of the Jacobian partial of x. Now this is what we want. Because in that sense, we have the input of the x and then we output the value q. Excuse me. But the problem here is it is not an absolute movement. It is an incremental movement. It is a partial of x, or in the sense we can say this is equivalent to Jacobian inverse times delta x. The change in x will result into a change in the joint angle q. Again, it is an incremental movement. Okay, well, in terms of control, it is good because the control equation is this. From here, you can change this into the difference of the desired x minus the actual x multiplied by some gain. multiplied by the inverse of the Jacobian. Then the result is how each joint will move. The incremental movement of each joint. Raise the hand. Okay, Mupare. Yes.
Yes, sir. I must have missed it.
Okay, wait.
Exactly.
Oh, you want to go now? You have a question? Yes. You have a question?
I'm sorry. Yes, I was saying Q is it?
Yes.
Can you hear me?
Yeah, I can hear you. Can you
Is
say? Okay, let's turn off our videos, I think. Okay, wait, let's turn off our videos so we can hear you. How do I turn on my video here? Stop video there. Okay. We cannot hear you, Mupate.
Okay, can you?
Yeah, now slowly we can. Okay, again, can you say that one more time? Yeah, we cannot hear you. Where is he? Okay, okay. So Mupate is gone. So, okay. Oh, here. Okay, come on. Can you complete your question?
Oh yeah, I was wondering what Q is.
Q is the angle. Yeah, we are saying here. Q is the joint angle. I didn't. It is the vector composing of, for example, theta 1, theta 2, theta 3, and so on. It is just a joint angle, a vector of the joint angles. Okay, because for here, for easy mathematical expression, instead of enumerating theta 1, theta 2, and theta 3, so we represent it with Q. Okay, sorry, we didn't say it clearly. And then for X also, instead of saying HX, HY, X, Y, and Z, for example, we represent it with just X. So that means this X vector represents X, Y, and Z, and including sometimes orientation, the vector of orientation. Okay, but let's not discuss about orientation because it's a different expression. So let's just say position X, Y, and Z. Okay, and then Q is the theta 1, theta 2, theta 3. Okay, so that's the forward kinematic expression. So you input theta 1, theta 2, theta 3 in terms of Q, and then you get X, Y, and Z. Okay, in terms of just the vector X. Okay, so I guess that answers the question. Mupati is gone, but let me finish by saying that this is how we control. In a sense, this equation here is the control equation. Okay, so the control equation is composed of the error of the desired X minus the actual X. The actual X is computed from here. Okay, that's the forward kinematics equation. The desired X is what you desire. You put it as what you desire for the robot to move and multiply it with that some gains, and then multiplied it by the inverse of the Jacobian. Now you will know how much angle each joint will move. And then that how much angle each joint will move is added to the current angle now, so that now you'll get the new joint angle. That's it. Okay, so this is just an overview of how we are going to implement the control equation in terms of the hand position, because that is the meaningful action. So now the next thing to do to complete this information is for us to understand what is the Jacobian and how we compute the inverse of that Jacobian. Okay, so once we answer that, especially in terms of just the planar robot, then we'll able to control a planar robot so that each joint can move and we can visualize what's going on as the planar, as the hand of the robot. We'll ask the hand of the robot to go somewhere, and then we change the desired values, then it will go where we want it. Okay, we will do that in the next meeting. Any other questions? Okay, I guess everyone is silent. Only Mupati was asking a question. Okay, so what time? It's 4 o'clock already. I'm beyond my time. So let's just stop recording. Recording.